Hi all, welcome to AI Business Forge. So this channel where we explore how cutting edge AI technologies like generative AI are revolutionizing business workflows. I have created this channel to dive deep into how AI can automate processes, solve real world problems and streamline operation across various industries. From research in different domains to developing practical AI solutions. So we are here to forge a path towards smarter, more efficient business practices using the power of artificial intelligence. So in today's video, we are going to dive into the fascinating world of transformer models and how we can train them from scratch. So we know transformer models are the backbone of modern NLP. It powering tasks like translation, summarization, text generation, and a lot of tasks. So think about that. What make them special? It's nothing but its use of attention mechanisms, which allows the model to focus dynamically on different parts of the input at each layer. For this project, we will be building a transformer model that predict the most relevant next word based on a given input. We will use a custom vocabulary and tailored training corpus to help the model learn contextual relationship between the words. The goal is to give you a hands-on experience with how transformers work and show you how this technology can be applied to business solutions. Let's get started. First up, we need to load and prepare our input data. For this example, we will use a straightforward corpus of sentences. Our first step is to split the text into tokens, which we can do with a simple tokenizer function. So in simple tokenizer function, break down the sentence into individual tokens, which can be words or subwords. So inside this function, you can see that uh, it will convert the input into lowercase and split it based on the spaces. And finally, this create a list of tokens and our model can work with. So this is basically the output of that simple tokenizer function. I have given the input as who are you, and it's returned back a list of token. Okay, so next we need to convert these tokens into numerical representations that our model can understand. This is where we build a vocabulary, a dictionary that maps each word to a unique index. So for that, we're using build vocab function. This function establishes a mapping between each unique token and its corresponding integer index. So in this function, you can see it will loop through the tokenized sentences, assigning a unique integer into each new word, which will also include the special tokens like pad, start, end, unk. It's representing the padding, starting, ending, and unknown words respectively. So finally, this is our output from vocab function. See, the each word is connected to the index so that we can this model can identify the number. For example, here we have the tokenizer ORU, and it will convert it into respected token numbers. For example, 12, 45, or 88. So this will be basically the output which expect by this function, by the next function is called prepare data. So in prepare data, this function transforms tokenized sentence into a sequence of indices, maintaining uniform length through padding or truncation. So the each input sentence get tokenized and each token is mapped to its corresponding index in the vocabulary. If a sentence is shorter than the maximum length, we apply padding. If it is longer, we truncate it. So finally we got the output like this. For example, I have already shown you that this 12, 44, 88. So this is the final output from the prepare data function. Now let's dive into the heart of the model, the transformer architecture. It consists of multiple layers, each serving a distinct purpose. The data flows through the model, starting from tokenization, moving into embedding vectors, positional encoding, encoding, and finally decoding to produce the outputs. So here is how the data flows. After tokenization, each token is transformed into embedding vector. Embeddings are dense vector representations of words. It allows the model to capture the meaning and relationship between the words in a numerical format. So this is crucial because it helps the model to understand the context. Next, we add the positional encoding to these vectors to retain the information about each token's position in the sequence. These embeddings then pass through multiple encoding layers where each layer includes self-attention, feed-forward networks, layer normalization, and residual connections. During decoding, we follow similar principles, but only difference is adding cross attention layers that let the decoder focus on the encoder's output while generating the predictions. So, first we just go through the positional encoding class. This class adds the positional information to the input embeddings. It enables the model to understand the order of the tokens in the sequence. See, in this class, it generate sinusoidal values based on the token positions, which are added to the token embeddings. This ensures that the model keeps track on token order, which is vital for any sequence based task. Let's take a closer look at the encoder layer. The encoder plays a vital role in transforming the input data into the series of high dimensional representations. This layer consists of two primary components, multi-head self-attention and a feed-forward neural network. See, both of which are key to capture the relationship between tokens and enriching their representations. The encoder layer class defines a single layer of transformer encoder, which is responsible for processing input sequence and generating contextual embeddings. In the forward method, the input sequence is first passed through the multi-head self-attention mechanism. Self-attention allows the model to compute attention scores between each token and other tokens in the sequence. It helps the model capture dependencies at different positions in the input. So in this step, each token attends to all other tokens by computing a weighted sum of token representation. The attention scores are computed by taking the dot product of the query and key vectors, scaling them and passing them through a softmax layer to normalize the scores. This result, the values are then used to weight the value vectors. So multi-head attention mechanism split the attention process into multiple heads, each focusing on different aspect of the input data. By doing so, the model can capture more complex patterns and relationships. So each attention head process different portion of the data in parallel, and the result from all the heads are concatenated to form the final attention output. After the attention mechanism, the encoder uses a position-wise feed-forward neural network (FFN) that is applied to each token independently. The FFN consists of two fully connected layers with ReLU activation in between. This helps transform the attended tokens into richer representations, allowing the model to learn complex features for each token. So the residual connections are then applied to maintain a strong flow of information through the network. In other words, we add the original input of each layer to its output to preserve information and prevent vanishing gradient during the training. So finally, layer normalization is used to stabilize the learning process and improve the training efficiency by normalizing the input features to have zero mean and unique variance. So let's discuss what happens in each layer. In self-attention layer, takes the input tokens, applies multi-head self-attention and generate attention output by capturing the relationship between the tokens. In feed-forward layer, transforms each token representation using a feed-forward neural network to further enhance its feature space. In residual connections and layer normalization, combines the original input with the attention and FFN outputs and normalize the result, ensuring better learning stability. Next, we examine the decoder layer. Unlike the encoder, the decoder also incorporate a cross attention mechanism in addition to self attention. This enables the decoder to focus not only on the previously generated tokens but also on the entire input sequence processed by the encoder. This is crucial for tasks like translation, where each output tokens must be generated while considering the entire input sequence. So the decoder layer class defines a single layer of the transformer decoder, which is responsible for generating output token by token, while attending to both the previous output and the input sequence. In the forward method, the decoder first performs self attention on the input sequence of tokens it already generated, for example, the target tokens. This helps it understand dependencies between the output tokens that have been generated so far. So the self attention mechanism in the decoder works similarly to the encoder, but it applies a mask to prevent the decoder from attending to feature tokens. This mask ensures that at each step of decoding, the model can only see previously generated tokens, enforcing an auto-regressive generation process. Once the self-attention is applied, the decoder introduces the concept of cross-attention. In this step, the decoder attends to the encoder's output. It computes the attention scores between each token in the output sequence and every token in the input sequence. This allows the model to refer back to the input when generating the next token, ensuring that the output sequence is properly aligned with the input. So the cross attention is crucial for tasks like machine translation, where it is important for the decoder to consider the entire input sentence when gathering each word in the output. After cross attention, the decoder, like the encoder, applies a position wise feed forward network. This further processes each token's representations, enhancing its features and making it uh, ready for output projection. So let's summarize what is happening inside each layer of decoder. The self-attention layer, the decoder applies the self-attention to the sequence of tokens it already generated, enabling it to understand the relationship between those tokens. Next, the cross attention layer. The decoder performs cross attention to attend to the entire input sequence, ensuring that it considers the input sequence while generating output tokens. Next is feed forward layer. In this layer, the token representations are further transformed using a feed forward network to enhance their feature for output generation. Residual connections and layer normalizations. Just like in the encoder, the decoder applies residual connections and layer normalization after each component, ensuring information flow is preserved and training stability is maintained. Now that we have explored the individual components, let's bring everything together by initializing the transformer model. So the transformer model class, it initializes the overall transformer model, including both encoder and decoder components. The model accepts hyperparameters like the number of layers, model dimensions, and the number of attention heads, etc. It initiate the encoder and decoder layers accordingly. So let's go through the hyperparameters. First one is SRC vocab size and TGT vocab size. These define the size of the source and the target vocabularies respectively, determining how many unique tokens the models can handle. The D model represents the dimensionality of the model, indicating the size of the embedding for input tokens. Num heads specifies the number of attention heads in the multi-head attention mechanism, allowing the model to focus on different parts of the input simultaneously. Num layers specifies how many layers of encoders and decoders the transformer will utilize. DFF represents the size of the feed forward network hidden layer, which is usually larger than D model for more complex transformations. For dropout, this is a regularization rate that helps to prevent overfitting by randomly dropping a fraction of neurons during training. With the model initialized, we can now proceed to train it. We will define our training loop, which involves the executing forward pass through the model, calculating the loss, and optimizing the weights. So let's roll up our sleeves and get into it. In this session, we will implement the inference functionality to predict the related words based on a given input word. The inference function is designed to take a single word as input and return multiple predictions of related words from our trained transformer model. The inference function predict the next related word based on a input word using the trained transformer model. It take a single word as input and generate a list of predictions by iteratively feeding the model's output back into itself. The first, we define how many predictions we want to generate. Look into this function, you can see. Let's say five related words. We convert the input words into its corresponding token index using our vocabulary, and then if the word is not found, no worries, just use the UNK token to handle unknown words gracefully. Then next up, we prepare the input tensor by adding the start of sequence token SOS, followed by the token index of the input word. Then we move this tensor to the same device as the model to ensure everything runs smoothly during inference. Now let's get into the exciting part, the generating our prediction. We use a loop to iterate and obtain multiple predictions. In each iteration, we feed the current input into the model, get the predicted output, and sample the next word based on the model probabilities. Finally, we convert the predicted indices back into words using our vocabulary. And we have our list of related words generated by our trained transformer model. We have gone through the entire process of training a transformer model from scratch, from data preparation to generating predictions. I hope this walkthrough has been both insightful and inspiring you. If you enjoyed this deep dive, make sure to like, share, and subscribe for more exciting generative AI workflows and real world use cases that I will be uploading soon. Thanks for watching. Bye bye.